Assalamualaikum. Welcome to our project video. The name of our project is Single Phase Sine Wave Inverter. I am Sheikh Muni Hussain. Along with me in Group 5, there are Jahidul Haq Imam, Shafin Salman Ahmed, and Azrul Islam. At first, let's get introduced with DCS inverter. An inverter is a circuit which converts DC voltage into AC voltage. Generally, lower DC voltage is converted to higher grid voltages using DCS inverter. In this project, we used full bridge inverter whose circuit is shown here. Our designed output voltage is 220 volt AC. Now we will look at our hardware design along with Arduino Nano that is used for creating gate pulses for MOSFETs, resistances, capacitors, transformers, DC are used. Next, we will look at the output that was shown at oscilloscope. Here, the output peak is lowered by voltage divider circuit for output voltage waveform shape visualization purpose. The output is not a pure sine wave as we can see here. There are two reasons behind this. The capacitors we have used are very small. The capacitor is of zero point 0.1 microfarads. That's why the output was not filtered out clearly. Another reason is the switching frequency. The switching frequency we used here were not enough to get smooth sine wave. Increasing the switching frequency would result in a beta sine wave. Our next group members will discuss the software parts one by one.
At first, we will describe the inverter circuit. A DC voltage source is used, and in parallel to it, a DC link capacitor is used to keep the input voltage constant and to resist any sudden change or spike in the input voltage. Next, there are 4 switches arranged in a single phase full bridge setup, with gate pulses being provided to the switches. The gate pulses will turn on the switches kept in alternate positions as shown in here. When the gate pulse A is provided, the switches getting this pulse will be on and the voltage across the load will be the positive half cycle. Similarly, when the gate pulse B is provided, the switches getting this gate pulse will be on and the output voltage across the load will be the negative half cycle. Next to this, there is an RLC impedance for filtering out all the unnecessary harmonics. After this, across a resistance, the output voltage is seen with the help of a scope. Here we can see that the output voltage we obtain does not match our desired voltage of 220 volt. So, to change it into a desired voltage of 220 volt, a step-up transformer is used and the output of this transformer is seen with the help of another scope. Here we can see that the output of this circuit matches with our desired output voltage.
So now we'll see the gate pulse generation circuit. Here is the triangular wave, which is the carrier signal. And this is the sinusoidal wave, that is the reference signal. We have used sinusoidal pulse width modulation SPWM technique for generating the gate pulses. The carrier and the reference is compared and the gate pulses are generated and the pulses are then fed into the circuits. So these are the gate pulses that we have generated. At first, we took the sinusoid's amplitude 0.9 and got output voltage around 13 volt. Output is not exactly 15 volt as per the input voltage due to some losses in the circuit. Then we can change the modulation by changing the amplitude of the sinusoid. So from here, we can change the value of the amplitude of the sinusoid. If we make the amplitude of the sinusoid 0.5, we get output voltage like this. Then if we want to see the case of overmodulation, we can change the amplitude here around 1.3 and that will give us the case of overmodulation. So now if we see the circuit, we get output voltage like this. We can see the output is clipped at 15 volts because the input to the inverter circuit is 15 volts. So the output is always clipped at 15 volts because this is not a boost inverter.
Now in our simulations of our output voltage magnitude depends on the change of the input voltage. Say if the input is 15 volt, if we look at the output magnitude, it is almost equals to 13.5 volt with 0.9 modulation index. Now here we change the input voltage to 20 volt, and if we look at the output voltage, it is almost equals to 18 volt. So if we want to maintain a fixed 220 volt output at the secondary winding of the transformer turn ratio has to be changed every time when we change the input. But it is not possible to do so in real life situation. So a viable solution could be introducing a PI controller. So here we have implemented a model PI controller which is taking a sinusoidal reference of about 10 volt amplitude, which is almost equal to our expected output here. In real life, this reference could be taken from a grid. Now, if we compare the reference of our output, that means the load voltage, with the sinusoidal reference, and then pass this arrow through this PI controller to mitigate it, then it will generate a reference signal eventually. Then we will compare this reference signal with this triangular carrier signal to generate the required gate pulses. Now, again, we will provide the input here, that means the initial 15 volt and 20 volt. Here the input is controlled by the MATLAB variables. So at first we set it to 15 volt, that means the input is 15 volt and the corresponding output was like that. So we can see that the output is almost equals to 10 volt. Then we change the input to 20 volt and observe the output at the sink. Here we can see that the output didn't change, it is almost equals to 10 volt still. Thus, if we use a transformer with a fixed turn ratio 10 by 220, we'll get the output voltage at the secondary winding equal to 220 volt. The change in the input will not have an effect here as long as it is higher than the 10 volt. Thank you all for hearing us this far.